Good evening. My name is Natalia Fedorczak, and I am a student project manager at the Clark Forum for Contemporary Issues at Dickinson College. Before we begin, I would like to take a moment to acknowledge that Dickinson College is on the unceded lands of the Susquehannock Nation. We acknowledge the many Indigenous peoples that lived with these lands, as well as the thousands of Indigenous children forced into the Carlisle Indian Industrial School starting in 1879 as part of a federal cultural eradication effort. On behalf of Dickinson College, the Clark Forum, the Departments of Biology, Chemistry, Data Analytics, Earth Sciences, Environmental Studies, Mathematics and Computer Science, Psychology, Physics and Astronomy, and the Churchill Fund, I would like to welcome you to the 71st Annual Joseph Priestley Award celebration, opening the infrared treasure chest with the James Webb Space Telescope. This program is part of the Clark Forum's Leadership in an Age of Uncertainty series. There will be a question and answer session immediately following the program, so please hold all questions until that time. The Clark Forum welcomes differences of opinion expressed politely, thoughtfully, and succinctly. Disruptive behavior or harassment of the speakers, members of the Dickinson community, or audience members will not be tolerated. As a show of respect to our speakers and everyone in attendance, please stay until the end of the program, including the question and answer session. At this time, I ask you please silence all cell phones and other electronic devices. In the event of an emergency, please know that accessible exits are located on the west side of the building. Following the lecture and the Q&A session, we invite you to join us in the lobby for light refreshments. And now, please join me in welcoming Provost, Dean of the College, and Professor of History, Neil Weissman.
Good evening and welcome. It's my honor to welcome you to the 2023 Joseph Priestley celebration. The annual celebration of the Priestley Award is always one of the highlights of the college's academic year. This year marks the 71st time that the award has been presented at Dickinson. Normally, it's done by the president, but President Jones is traveling this weekend, it says on college business, recruiting students, so we all wish him very, very well. And when I heard this, I was more than happy to step in for him as the host of tonight's lecture. And it's actually particularly meaningful to me since it will be my last time doing this as provost of the college. For each of these 71 years of the event, the college community has gathered to present this award to a distinguished scientist in memory of Joseph Priestley, the discoverer of oxygen and a close friend of our founder, Dr. Benjamin Rush. The presentation of the award demonstrates the college's strong and enduring commitment to the advancement of science as an integral and central focus of the liberal arts curriculum. In fact, we don't refer to it as liberal arts. For us, it's liberal arts and sciences. The commitment is demonstrated in our vibrant science faculty and in our state-of-the-art science facilities. Dr. Rush, as he was founding the college, sought out other revolutionary thinkers of his time, including Priestley. Priestley was born near Leeds, England in 1733. He prepared for a career in the ministry, but he developed a deep and active fascination with science. In pursuing this interest, Priestley turned to investigation of what he termed different types of air, explorations that led to the discovery of 9 gases, including sulfur dioxide, ammonia, carbon monoxide, carbon dioxide, and a gas that was later named oxygen. Recently, it has even been claimed that in exploring oxygen, Priestley invented ecology. He discovered the relationship, so it's claimed, between oxygen, a physical thing, and life. This is probably a bit of a stretch, but at sustainability-focused Dickinson, it's a stretch that we can live with. I can't resist adding, I just can't resist, that Priestley also invented carbonated beverages, although the patent actually went to Johannes Schweppes, and it is also claimed that Priestley invented the eraser. Priestley's increasing unorthodox views on theology, coupled with his outspoken opposition to the English slave trade and his support for the American Revolution, ultimately forced him to flee England for America in 1794. Once here, he soon formed a close friendship with the nation's leading physician, and that was Dr. Rush. Although Priestley died only 10 years after arriving in America, his connection to Dickinson College continued when we acquired much of Priestley's equipment, thereby ensuring that Dickinson students would have state-of-the-art scientific instruments with which to work. You can see the equipment in our library's archives. These items represent some of the earliest examples of student-faculty research at Dickinson. As I noted earlier, 70 distinguished scientists, including 16 Nobel laureates, have received this prestigious award previously, and tonight that number increases to 17. The list of early Priestley awardees includes Harold Urey, discoverer of deuterium, Linus Pauling, recipient of a Nobel Prize in Chemistry and also the Nobel Peace Prize, nuclear physicist Edward Teller, co-discoverer of DNA Francis Crick, and astrophysicist Carl Sagan. More recent honorees include Vinton Cerf, a computer scientist who contributed to the creation of the internet, Joan Steitz, a molecular biologist known for her foundational work on aspects of RNA and her advocacy for women in science, and our most recent recipient, Luis von Ahn, for his pioneering contributions to human computation. Now, to introduce our newest recipient of the Joseph Priestley Award, I'm pleased to introduce Professor Brett Pearson from the Department of Physics and Astronomy.
Thank you, Provost Weissman. It is my pleasure to introduce Dr. John Mather, Senior Astrophysicist and Senior Project Scientist for the James Webb Space Telescope at NASA's Goddard Space Flight Center. Dr. Mather received his bachelor's degree in physics from Swarthmore College, a liberal arts and science college just down the turnpike from Dickinson, before completing his PhD at the University of California, Berkeley. He did a postdoctoral fellowship at the Goddard Institute for Space Studies at Columbia University, where I'm guessing he may have frequented Tom's Restaurant or Monk's Cafe from Seinfeld fame, which I believe is located on the ground floor of that building. He then moved to the Goddard Space Flight Center in Maryland, where he's worked on many projects over his career, most notably leading the Cosmic Background Explorer, or COBE mission, as well as the James Webb mission. Many of you are likely familiar with the James Webb Space Telescope, and the released images have been both beautiful and provocative. Dr. Mather's work focuses on using infrared spectroscopy aboard the JSWT or other observatories to help understand our universe. His research addresses the big questions that have long captured human attention as we look out into the cosmos, covering topics like the Big Bang, the formation of stars and galaxies, and possible life on other planets. I'm sure we'll hear about some of these this evening. Outreach is an important aspect of NASA missions, and Dr. Mather is an enthusiastic public educator, named by Time magazine as both one of the 100 most influential people in the world and one of the most 25 influential people in space. Dr. Mather responds to questions from the public on NASA Twitter and appears on several different YouTube channels discussing a range of topics. The success of this outreach is clear. In my junior seminar course last semester, students chose the James Webb as a topic for us to discuss during one class session, and I loved hearing about instruments like the near-IR spectrograph and the science missions of looking at first light and galaxy assembly. Dr. Mather also agreed to host an Ask Me Anything thread on Reddit, which certainly demonstrates some bravery. The questions look great, and one high school student interested in studying physics asked if you've ever regretted your decision to do physics as a career, and then added that their parents wanted them to also ask if you ever couldn't find work in your field of study. So, tonight, we recognize Dr. Mather with the Joseph Priestley Award, an honor that joins many other accolades, of which I will mention just a small sampling. He's a member of the National Academy of Sciences. His Kobe and James Webb missions are two-time winners of the National Air and Space Museum's Michael Collins Trophy. Dr. Mather received the Benjamin Franklin Medal in Physics, the Gruber Foundation Prize in Cosmology, and the John Scott Award from the City of Philadelphia. In 2006, Dr. Mather shared the Nobel Prize in Physics with George Smoot for their discovery of the blackbody nature of the cosmic microwave background radiation. And in 2007, he received NASA's Distinguished Service Medal. It's an honor to add the Priestley Award to this list. I should mention that the Priestley does have a history of recognizing leaders in astronomy and astrophysics, including, like you heard, Carl Sagan, also Philip Morrison, Arno Penzias, Jocelyn Bell Burnell, and Joseph Taylor. We're extremely pleased to have John Mather with us here this evening. Welcome to Dickinson.
Okay, the Priestley Award includes a bronze medallion with a likeness of Priestley. I don't know why I'm holding it up because you can't see it at this distance, but it is, take my word for it. And here we go. It's in honor of your extraordinary accomplishments in science. And let me read the citation that goes with it, which reads, Dr. Mather receives the Joseph Priestley Award for his precise measurements of cosmic microwave background radiation, informing a new era of precision cosmology, unveiling both the birth and fate of the entire universe, as well as his leadership of the James Webb Space Telescope mission. Congratulations.
Thank you. Thank you.
Set it down here.
I just need to look at him.
Okay. Thank you. Well, let's see if we can do this part. This is the magic part. So thank you very much for the lovely recognition. And I'm astonished to see this long list of amazing people that I have succeeded. And I actually have met some of them, going back to Edward Teller. I got a scholarship interview in his kitchen, and I thought I had failed. But I actually got the scholarship. Anyway, tonight I want to tell you all the secrets of the universe that I actually know, which is not all that many. So there is a picture of the great James Webb Space Telescope. It includes a gigantic hexagonal mirror made of beryllium coated with gold, so it can reflect infrared light very well. It is protected by 5-layer umbrella to keep it very cold. And it is a joint project of NASA with European and Canadian space agencies, and it has taken altogether 20,000 people to bring it off. My work on it started in 1995, but even before that, there were people who were already figuring out what we needed to do. So this is a very, very long cathedral project, almost, and I think it's been worth it. So what do I want to show you? Well, why am I so excited about projects like this? These questions have been on my mind since I was little. Where did we come from? How did we get here? What's the history? And are we alone? Of course, our opinions about these have changed since I started thinking. And if we're not alone, where are the neighbors? How close by are they? A serious change in perspective has occurred on origin of life. When I was young, it was thought it required either divine intervention or an extremely unlikely coincidence of physical situation. So I think today I would argue that it's something that would always happen given a chance. So we don't know, but that's my guess. And of course, everybody wants to know, can we go out and travel through space? And the answer is yes, we can go as far as Mars. But astronomers can go everywhere because we can take pictures and we can imagine. So people have been thinking about some of this a long time. Here is a statement from Lucretius. a poet, but a serious thinker. He was aware of the atomic theory in ancient times. And how would you know that things were made out of atoms? Well, you see your water glass evaporates and disappears. It must turn into tiny indivisible particles. That was some of the evidence, and I don't know how much more they had. But he was aware that big things are made out of little things, and that was a wonderful mystery story to tell. In this version, it even includes some acknowledgement of our linguistic capability of naming things. And anyway, so how does it really work? We are working on this. We have not finished answering his questions, but here's a little bit of my story. Just people like to know that people that I do what I do actually started somewhere. This is this farm where I grew up. It's far northern New Jersey. It's a mile from the Appalachian Trail, and the land looks a lot like it does here. It was a research farm for Rutgers University. My dad was studying dairy cows. And so in 9th grade, I learned about animal feeding experiments and analysis of variance. At any rate, I didn't grow up to be a student of dairy cows, but that's where I started. I learned physics from books that came around on the bookmobile a lot. So that was then. A little bit more history, what happened back in the 40s. Well, here's Lyman Spitzer, a very famous astronomer. In 1946, the war was over with Europe and Japan, and he wrote a little article that said we should build telescopes in space, not only to look down, because he's writing this for the Rand Corporation, but also to look up, to do astronomy. So he was right, and we have built telescopes, and we've even named one after him. Then who's next in the picture? Sir Fred Hoyle. Sir Fred, wonderful cosmologist, very ingenious thinker, and he has confused the heck out of our subject for a long time because he named the Big Bang Theory. And if you hear that story, you can hardly avoid thinking of a firecracker. So people tell this story wrong. We'll come back to that. And then, in 1946, he turned up. Me. So a year and a day after Hiroshima, so I'm a child of the atomic age, which makes a person think too. So what else happened? A little after that, these guys on the left, Herman on the most left, Alpha on the right, they were working on understanding the Big Bang Theory that hadn't yet been named, and they calculated the universe should be filled with heat radiation, and it would now be down to a temperature of about 5 degrees Kelvin, 5 degrees above absolute zero, and they were right. But nobody went to look. It was thought to be impossibly difficult. If somebody knew there was a Nobel Prize waiting for them, maybe they would have tried, but it would have been just really hard. So nobody tried. In 53 or so, I was taken to the Museum of Natural History in New York City to the planetarium show, and people believed we would see the canals on Mars. Well, they aren't there, unfortunately for us, I suppose. How many people have heard what the canals really were in the eyeball of the beholder? So that's the arteries and veins in the back of somebody's eye. Fooled them. So also, in 57, the Sputnik went up and it scared the bejesus out of people here. Even though it was not a surprise, we had been told at least 25 times that this was going to happen. Nevertheless, people got it when the projectile goes flying over the country. Okay, we realized that not only could they send bombers, but they could attack from above. This was the Soviet Union in days when we had been taught as children, in case of nuclear attack, hide under the desk. So that was, you didn't have to be old to know that wasn't going to work. But the United States responded by creating NASA, among other things. Not only did they invest in all the war stuff, but they started up NASA. So that's our charter from 1958. And it authorizes, among other things, that NASA is supposed to tell you what we're doing and give you the results. And I think we may be the only federal agency that has that in the charter from Congress. So anyway, we're doing it. Some agencies don't have that, and it's a bit of a struggle for them. But at any rate, then we've got Jack Kennedy here, and he is speaking at Rice University and telling us...
But why, some say, the moon?
Yeah.
Why choose this as our goal? And they may well ask, why climb the highest mountain? Why, 35 years ago, fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
Well, I loved what he said. But I love it more now than I did then. At the time, I thought, well, that's just politics. I'm not interested. But now we can see what a difference it made. The Apollo program enabled us to spend a fortune on high technology stuff, and we basically, you can say, almost everything we have today that's descended from that comes from the fact that we were opposed to the Soviet Union, and we made a huge investment in people like us, scientists and engineers, to defend us, and we have. So we're not done yet. But anyway, here is James Webb, the man that we named the telescope after. He was the man who told Jack Kennedy how to do this. And there's some lovely secrets about this. One is, on the taxi cab on the way to see the president, he decided to double the budget. And then it was just barely enough, because he knew that some of us are just too optimistic. You cannot trust that scientist and that engineer to get the budget right. So he was correct about that part. Anyway, and he also said, Jack Kennedy, we need to send science missions. We want to start up probes to the outer solar system. We'll go send something to try to land on Mars, and he did. So got a lot of things good going for him. Now, stepping back to science, we look back in time. Everybody does. You look at things as they were when light was sent to you, not as they are right now. So how do you know? Well, you just have to see how far away something is, and you know the speed of light, so you know how far back you're looking in time. So if you look at something really close by, it's a very short amount of time. If you look at the sun, you see it as it was 500 seconds ago. If you could look all the way back towards what we call the Big Bang, almost 15 billion years back in time. So we need to know geometry in order to know the time that we're looking. So how do we know the geometry? We measure distances by surveying. The ancient Greeks would have been able to do both of these calculations, I think. First one is just triangles, and the second one is compare the brightness of two things. One is the brighter one is closer to you, and they would have understood this argument if we'd shown them, and maybe they even did. I don't know. Anyway, they were good enough to measure the size of the Earth and even to estimate the distance to the moon, but they couldn't get the distance to the sun. It's too far. So pretty good at that. We also have a way to measure whether things are coming toward us or going away from us, something called the Doppler shift. If you are driving down the highway and you hear a motorcycle coming up behind you, and then it goes past you, you can hear the pitch of the engine drops as it goes. This is an equivalent story in sound waves. Anyway, if something is going away from you, you get the waves come less frequently, and the wavelengths are longer. So now we can measure the rate of things going away from us by this technique. And so anyway, we did. So starting back in 1929, we've been having graphs of the expanding universe. So the story that the universe is expanding is almost a century old. Edwin Hubble drew us this picture. It was actually predicted by Georges Lemaitre, who was a lovely guy. He was a Belgian priest, as well as having a PhD from MIT. And he predicted this, that would happen, but he did not make any claim for having to be recognized for this. He was a modest guy, and he just wanted to understand. He even got to see the Pope. And the Pope said, doesn't this support the picture we have in the Bible? And he is reputed to have said, well, we don't think we should mix these two subjects together. So anyway, what happened after that for me? I went to, as was mentioned, I went to work in New York after my thesis project at Berkeley had failed. The introduction didn't tell you that part. My thesis project at Berkeley failed to measure the cosmic microwave background radiation, at least on the first flight. I got a job at the NASA lab in New York, and there it is, over Tom's Restaurant. And that's where I was when NASA said, we want proposals for new satellite missions. Boss, my thesis project failed. We should try it in outer space. So that's kind of nervy, and I didn't think it would ever work, but it did. So 15 years later, it was launched into space, and it worked beautifully. And here is an artist's concept of it in outer space. It looks more or less like the sketch that we draw in the first days. So what did it do? It had instruments to measure the color of the heat of the radiation, that is to say, how bright is it at each different wavelength, and also instruments to measure is it equally bright in all directions, which turned out to be really important, because here's the map of that. This is the entire sky flattened out onto a flat surface. So you can see it, and it's covered with hot and cold spots, which are not very hot and not very cold, but almost at the limits of what we could measure in those days, and they mean something. They mean that the early universe was not exactly the same everywhere. We know it's expanding, oh, that was well known, but how come are we here? So if it were completely smooth and symmetrical, we would say, what could possibly happen to make it unstable to form a galaxy out of all that primordial material, whatever it was? The answer is no, it wasn't exactly the same. So there are places that are a little more dense than average. The gravity in those areas is a little stronger than elsewhere. It's enough to stop the expansion of the material and pull it back together. So we're here because of those spots. Thank you, spots. When Stephen Hawking saw that picture, he said that was the most important scientific discovery of this century, if not of all time. Okay. I'm glad we got it, because from us as the experimenter's point of view, this was just at the limit of what was possible for our equipment. But now we know most of those spots come from something astronomers call cosmic dark matter, and nobody can see it, but it has gravity. And the pattern is also affected by cosmic dark energy, which is the name we give to something that makes the universe accelerate in expansion. And so combining all of this, it's pretty interesting. So I never knew how much would happen after that, but anyway, there's me showing my spectrum, the one that was mentioned earlier, and there's me with the king getting my diploma in Stockholm. So had a good time. I've been giving versions of this talk for a long time. So now I want to sort of talk just momentarily about the misconception that everyone has, apparently, that the universe was compressed into a point. Well, no, you actually have no idea what this would possibly mean. The universe appears to be infinite, without end, in all directions, and always was. So you can't compress infinity into a point, sorry. So the public journalism that tells you what is the Big Bang, they just did not get it, I'm sorry. But it's partly Sir Fred Hoyle's fault. So if you didn't understand it before, it's not your fault either. So just jumping ahead, so how do we know what's happening then? Well, of course, we've built the Hubble Space Telescope. It was launched just a few months after the COBE satellite, and we took wonderful pictures with it. And it's almost 33 years old now, next month. Anyway, it's still working beautifully because, of course, we sent astronauts up 5 times to upgrade it and fix it. And it's taken beautiful pictures. And right away, after they got it working, they said, by the way, we have a big surprise for you. The galaxies did not grow the way we said they would. Astronomers were very convinced that galaxies could only grow slowly. And they got this wonderful picture, and bam, they're everywhere. So they wrote a book, and they said, please build us a better telescope that can figure this out. So here's the telescope they asked for. This is the James Webb Space Telescope, the JSWT. Just another image of it, telling you this time that our big contractor is called Northrop Grumman, that we have instruments in the telescope from four instruments that come from Europe, Canada, and the United States. Operations is in Baltimore, as we do for the Hubble Space Telescope. And it was originally planned for 5 years of life. That was the requirement. But we got a perfect launch. This is the telescope observatory going up in French Guiana on Christmas morning, 2021. And so now we are hoping for 20 years of life. And that's because the rocket went exactly where we hoped it would go. So thank you very much. That's a European rocket, by the way. It's called the Ariane rocket. So we put it way out there at around a place called the Lagrange Point 2, which wasn't discovered by Lagrange, but it was discovered by Leonhard Euler, who had a pencil for a calculator. And anyway, this is a special spot because if the telescope is out there, the sun, the earth, and the moon are all on one side. It means you can put up an umbrella, the telescope will be protected, and it'll be cold. The telescope will get very cold. And we want it to be cold so it doesn't send out its own infrared light that we're trying to measure. And then I guess everybody knew we were worried about the unfolding of the telescope because it had hundreds and hundreds of things that could go wrong. So here's our telescope unfolding itself in outer space. We send commands out to it. First thing is unfold the solar panels. We get solar power. Unfold the antenna. Now we're unfolding the structure that holds up that big umbrella, the sunshade. This takes place over 2 weeks. So this is not 7 minutes of terror like the Mars landing. This is us being very cautious for 2 weeks. So at everything that was done by command, we said, did that work right? And if it didn't, we had another way. But we never had to go to the backup plant, which means we really did a good job on the test program on the ground. So you look at that, you say, that's awfully complicated. It is, no question about it. But there seems to be no alternative. If you want this kind of information, you have to build this equipment. So there it is. It's doing its thing all by command. And the last step here is to unfold the telescope itself. And it is not quite ready yet to take pictures. At this point, it's still warm. It's not cooled down to the operating temperature. And it's not focused yet. So that whole process of setting up the telescope and getting all the equipment calibrated and ready to go and tested took altogether 6 months after launch. And ended up we were able to have the president announce the first data on July 11th last year. So now I want to show you why are we studying infrared light. So various reasons. One of them is that dust grains in space are opaque, but they're less opaque if you can use infrared. Okay, so why is there dirt in space? Because stars burn hydrogen and helium and they blow up and they liberate carbon, oxygen, nitrogen, iron. Everything you see around you came from nuclear furnace in stars that blew up. So how did that happen? Well, and also, there it is in space, preventing us from seeing inside the cloud where a new star is being born. So we just really still are pretty mystified about how stars are born, but even the infrared that the Hubble could do shows you it's a very different picture. So, you know, you can get a sense of this when you go to the airport and you walk through the scanner, they look through your clothes. That's longer wavelength light. They're using millimeter waves, which is a longer version of infrared. So anyway, it shows you new pictures because you can see through dust clouds. It shows you cool things. Now here's a star that's in the process of blowing up. And what we see there is a different picture in the infrared than we had before. I think the left side is the Hubble version and the right side is the Webb telescope version. So magnifying it a little bit, the infrared one on the right side shows actually there are two stars. When you really work out the details of why does this look so weird, there are probably 5 stars in there. So this is just a star getting old, and when it's used up all its fuel, the dirt comes out. Here's an even more dramatic example. This is a pair of stars, and every time they get close, it sends out another pulse of dirt and dust into space. And you see the rings that have been captured by our telescope picture on the left. So that seems to be the right story about this. By the way, just to point out, this says image processed by Judy Schmidt. She is a woman who lives in Modesto, California, and she likes our pictures, and she adjusts them, and so they look better, and you can see more in them because of what she does. It's not exactly science, but it's very informative for scientists. So thank you, Judy. So here's a third thing we use infrared for. This is because the universe is expanding. You can either say space is expanding or things are running away from us, but it appears that distant galaxies go away from us and the wavelengths that they send to us get stretched out. What started out as visible light or ultraviolet ends up as infrared at our telescope. So we need to build this infrared capability to study ultraviolet. So that's an example. So now let me show you the first picture that President Biden put out, July 11th. This is a cluster of stars called SMAC 0723, and it shows you several things. In the middle is a big bright fuzzy thing that's a galaxy, very, very massive galaxy, and several others. And we sort of knew they were there, no surprise there, but they have enough gravity in them to bend light. So Einstein told us gravity would bend light, and when we went to find out if his story was correct, we measured with the sun, and sure enough, the sun bends light by its gravity. Here we're using this as a natural lens that the universe has given us to magnify more distant objects. So those funny-looking streaks and arcs and the pink things in there are gravitational images of more distant galaxies. Sometimes a single galaxy appears 3 times. So then we use this as to help us see farther and better. Of course, it's a little tricky to figure out what's the magnification of this natural lens, but it's very, very powerful. And let's see, you might have been distracted by those things with the bright spikes sticking out. Those are just regular old stars. So they're not so exciting to us anymore. There are plenty of them. They get interesting when they do something, like they blow up, but when they're just sitting there, they're just in the way. So this is an example of one of the magnified images. That one on the far, these are 3 images of the same object. The one on the far right is the magnified the most, and we call this the sparkler because it's got all these little luminous things in it. Astronomers call them globular clusters because there are 100,000 stars huddled together in a small package. And we have some that you can see here with your own eye when it's dark. Anyway, we are really excited to discover that this seems to be the way that galaxies grew. They had vast numbers of these globular clusters even when they were very young. Here's a beautiful picture showing you galaxies in the process of merging. There are 5 galaxies in here. The one on the left is actually not related to the others. So we'll talk about the 4 in the middle. The 2 that are right in the middle are merging together. It'll take them a few 100 million more years, and they'll be mushed together into a new formless blob. And you can see they're interacting because there's arcs of color around them. That's where the gaseous material has collided. Galaxy has stars and gas. So when the gas collides with other gas, it gets cranked up to high temperature. It triggers all kinds of things to happen, like new stars are born. In the top galaxy, let's see if my pointer will point here. Yeah, anyway, there's a black hole in the middle of that one. And how do you see a black hole? Well, what you see is something very, very bright. Material is falling into the black hole, and it's getting compressed and heated to enormous temperatures. And so we see that. We don't actually see the black hole itself because everybody knows things fall in, they don't come out. That's sort of a definition. So we're seeing a black hole. We're trying to understand how they grow. Every galaxy seems to have one, just about. Our Milky Way has one that's about 1 million times the mass of the sun. Some galaxies have like 10 billion times the mass of the sun. We have no idea how this happened. Or maybe I should say we have a lot of ideas, but none of them are provable. So we've got to work on this to be able to tell you the story better. Here's a picture that's pretty as well as informative. The big one with the ring around it was the target. And the little red one on the upper left went straight through the middle of it. So we're seeing a splash. And what we're seeing is a burst of new stars have been born in that ring, and that's flying away from the center. So we're beginning to learn how stars are made by galaxies. Here's another picture that tells you about a galaxy. This is a galaxy that ordinarily looks like an ordinary spiral galaxy with a nice core and arms. When we get the infrared capability that we have, now it looks like slices through a sponge. So why is that? When new stars are born, they're bright and hot. They liberate immense amounts of energy. They push the material around them away. So those holes in there are made by the presence of brand new stars. So we're learning about how stars interact with each other and how they trigger the flows of material around. Anyway, it's a view that we never had, and now we're going to have to figure it out. Here's something we call the pillars of creation. And you've probably seen other versions of this picture that we got with the Hubble telescope. Now we have the infrared version and we can begin to see inside the clouds where stars are being born, and even a few are starting to burn through, and you can see them special and different. I guess I can't get my pointer over there, maybe. Anyway, that's obviously something brand new happening. So not only is it pretty, it's very informative for scientists. Here's one that I really love because we wanted to know how are stars born and how do they make planets. So here is one that's doing it right now. What we see is not quite the star. There's a star hidden right square in the middle of that pattern, and it's shining up and down, and it's surrounded by a disk of material orbiting around it, which blocks our view of the star itself. But that disk of dirt orbiting around the star is where new planets are being born. So come back in 100,000 years, there may be planets and no dust. So patience. So there are a lot of these out there to find, and so we're making some progress. Of course, we want to know, how about those planets? So we are looking at about 6 of them the first year of observing by the method called transiting. When a planet goes in front of the star and blocks some starlight, we can say, oh, I saw something happen. If it happens over and over again on a regular rate, you can say, now I know how long it takes to go around the star. And now we're going on to the next step, which is there any atmosphere? Does the starlight go through the atmosphere of the planet on its way to our telescope? And yes, it does, if there's an atmosphere. So far, we're working on small planets and big ones. The small planets have not yet showed up to have any atmosphere. The big ones do. So a planet as big as Jupiter, oh, of course it has an atmosphere. It's mostly gaseous anyway. So we get some of that. But we're a little disappointed, maybe not too surprised, that no small planets, Earth-sized planets, yet are known to have an atmosphere. So maybe the neighbors are a little farther away than we hoped. But we're not too surprised. So here's an example of what we call spectroscopy. You spread out the light of the star into its colors, different wavelengths, and now you look to see, well, how much light is blocked by the planet at each different wavelength. And in this case, we can identify lots of different atoms and molecules: sodium, potassium, carbon dioxide, carbon monoxide, water, sulfur dioxide. They're all in the atmosphere of this big hot planet. And we're not too surprised, but we know our technique works. So now we have to try again for the little ones. We have some beautiful pictures of the solar system. Here's good old Jupiter. Looks different this time. This time you can see that it has a ring around it. So all of the outer solar system planets have rings. And they're pretty. And they tell us something about what makes things orbit. So they have a shape because they're influenced gravitationally by the satellites of Jupiter. Sometimes, in fact, on this one, this ring seems to actually have a satellite embedded right in it. There's another one embedded right in the ring. So we can watch the big old red spot. It's not red when you use infrared colors. By the way, since you can't see infrared, we can't give you an infrared picture to look at. So we have to make up a color for you. So we do it usually in the same way. We put the shortest wavelength as blue, the longest wavelength is red, and then we can understand it as well as admire it. So there's a reason for this, but it's not always done that way. Here is another surprising picture. This is when we attacked an asteroid. We sent a probe called the Double Asteroid Redirection Test. We dropped a big bomb, actually not explosive, just a piece of metal. We dropped it on this asteroid, and it, of course, made an impact, and here we're seeing the debris coming out. So we need to do this so we can know, can we deflect an incoming asteroid that might have hurt us? We're just beginning. This is the first test we've made of getting an asteroid out of the way. So here is Titan. Titan's a satellite of Saturn. Titan is big enough to have its own atmosphere. It's the only one that has a lot of atmosphere. It has so much atmosphere that we are sending a helicopter to fly around on Titan. Around 2034. So that's not so far off, 11 years off. And we have pictures taken at different wavelengths. So this satellite is interesting because it has geology of sorts. It has lakes and rivers, hills, rain, clouds, and the rain, clouds, and rivers are all made of hydrocarbons like methane and ethane. So, well, do you think that's alive? I don't know, but nature has done an experiment. This is a place where water and hydrocarbons are existing together, and sunlight is coming in. Interesting things could happen. Here's another pretty picture. This one is Neptune with its satellites. So, like I said, they all have rings way out there. So, understanding how does that all work inside, that's pretty tricky. So I'm not able to tell you why does it look like that. But I can say, if you want to know a lot more about our satellite, our telescope, there's plenty to show you. So we are very live on social media. We have press releases that come out every week. I don't have it in here, but we just released, it's just been published that we did observe a little planet that orbited a small star, and sorry, that has no atmosphere. It's a definite measurement, there's no atmosphere on that one. So that's sort of the summary of the Webb telescope. Now I want to wave my arms a little bit about what do we do next. So we have lots of ideas for new telescopes that we're going to launch or build on the ground and tell us new things. So this one is going up next year, or this year actually, it's 2023. It's a European one. It's a small telescope about this big. They're going to hunt for dark matter and dark energy signs. Again, you can't see them because they're transparent, but they're going to take pictures of millions and millions of galaxies and do their math to calculate what is the dark matter and doing to that. Coming soon. Then there's an American telescope called the Vera Rubin Observatory. We're building it in South America, and we've named it after a woman astronomer who was the one to really demonstrate to us there is dark matter. And she did not get her Nobel Prize, but a lot of people thought that she should. So this is a telescope that's enormous. It's bigger than the Webb telescope, and they're going to survey their entire sky every 3 nights and send us a list of 10 million things that changed every night. So you don't think of the sky changing every night, do you? Anyway, it does. We're going to need a lot of graduate students or artificial intelligence or something to keep track of all that. We can barely handle the amount of data this is going to produce. So next year, we are sending up a telescope in space named after Vera Rubin, Nancy Grace Roman, who was the head scientist at NASA headquarters, head astronomer for a long time, a friend of mine, actually went to Swarthmore College before we went out. So this is a telescope to pursue the dark matter, the dark energy, and try to take pictures of planets. So not so far off. It's already in progress. We have the parts at Goddard, and we're putting them together. We have been asked by astronomers to please build a successor for the James Webb Telescope that's at least as big and more powerful, that would be capable of seeing Earth-like planets orbiting stars like the Sun. Actually, not just get a transit event, but see a little dot that moves around the other little dot and say, okay, now I see, now I really believe there's a planet, and we can get its spectrum, we can see what's in its atmosphere. And this is important because we think stars like the Sun are the best place to look. We just can't do it yet until we get this kind of telescope. So that is coming. I don't know how long it takes, maybe 10, 20, 30 years. I hope to still be here when we launch it. On the ground, our friends are building enormous telescopes too, much bigger than we can put into space. The one on the top right is actually under construction. Fully funded European project, 39 meters across, almost as wide as a football field, 6 times as big as the Webb. We've got to be able to use it. But unfortunately, American astronomers have no access, unless you're really friendly with a European astronomer. So we are leading 2 projects in the US that are shown there, the Giant Magellan Telescope with 7 mirrors, and the 30-meter telescope is supposed to go into Hawaii, but neither of them has enough money to go yet. And this is a reminder that although we spend a lot of money on science, we don't spend enough to build these telescopes. And the National Science Foundation just doesn't get enough to do big projects. But there's no other way. So we're stalled until something can happen about that. So if you have a congressperson, you know who to talk to. So not just astronomers need big projects, but every area of science has big projects in mind. And so general increase would be really cool. So I want to sort of wrap up with some wild ideas I've been working on. We have something called adaptive optics. The atmosphere of Earth is very turbulent. When you look across the summertime, you look across the fields, you see everything is shimmering in the sunshine. Well, we don't like that for astronomy, so we have a way of correcting for that with adaptive optics. You focus on a star or something up there, and you diddle with your mirror and correct anyway, you can get it to focus better if you can change the shape of your mirror very fast. So, but you need something to focus on. So we've mastered that, sort of. If you go to the eye doctor, they've got the same technology. Your eye isn't exactly stable, and it's also imperfect. So your eye doctor wants to see the back of your eye a little better, so we give them this technology. And the connection is a little closer than I would have thought. The person who figured out how to measure the Webb telescope mirrors is the inventor of the technology you now get in the eye doctor's office. So it's not spin-off, but it's a person that knew how to do one thing and then invented the other. So that's pretty cool. So my idea that I've been working on lately is to fly a satellite laser and shine it down on the telescope to be a star that you could focus on whenever and wherever you want. So if you can't focus on the star for some other reason, you have one you can use. So we can put it there, and it's not that hard to build or buy. We could buy all the parts today and do it if somebody said go. So that's a pretty cute idea. It's not ready yet, but it's almost ready. And here's the wildest idea. If I want to see those little planets orbiting around a star out there using a telescope on the ground, I need something I don't have. I need something to block the starlight so I can see the planets. Starlight is 10 billion times brighter than the planets. Oh, that's an awful lot. So please block the starlight and don't block the planets. So the answer could be build something as big as 2 football fields, 100 meters across, cast a shadow of the star onto the telescope on the ground, and don't block the planets. So it could be done. In principle, it could be done. So this is a fun project to work on. And again, it's unlikely to happen in my lifetime, but I'm working on it. So if we could do it, we could get a picture of a solar system out there in 1 minute. It's worth trying to figure this out. Even if we can't do it, and we should try. So the curious thing is, if you could do it, you could really see signs of molecules that tell you it's like Earth. You could see water and oxygen in a spectrum of a planet way out there. But everybody wants to know, well, can we get out of here? And the answer is that, well, yes, but not very far. We can go to Mars. The robots can go anywhere. And they already have. They've been to all of the planets, to some asteroids and comets, and some of them have brought pieces back home for us. The computers are getting better. They're not quite up to being like HAL in 2001, but they could be not so far away. If you ask ChatGPT, can I open the door? It could say no. So we need to learn about this. So I don't know how far the robots can go with our help or without. It's not totally impossible that they could take over. But anyway, if they do, they'll still have an interesting challenge because it'll take them forever to get to the nearest other star. So even if we have smart robots in the AD 1 billion, they will still need to be very patient to get themselves to the next star. Anyway, so I'd like to be here when that happens. Thank you.
Thank you so much, Dr. Mather. We will now begin the question and answer portion of tonight's event. So just a reminder, because this event is being recorded, please raise your hand and wait for for a microphone to reach you prior to asking your question. We would also like to remind you to please keep your questions brief and return the microphone after asking your question out of respect for both limited time and the questions of other audience members. Now, we always reserve the first question for students, but after that, we welcome questions from anyone and everyone. And with that, we are looking for our first question.
I just wanted to say thank you so much for coming out. This really means a lot for a lot of the students here, and everything that you had to say was really valuable, and I really appreciate that. This might be a little bit of an unorthodox question, but I don't know if you've ever been asked this before, but what are your thoughts about the conspiracy moon landing?
Oh, I'm sorry, I actually couldn't hear that very well, but because I'm a little deaf, sorry. So could you just say it again?
Sure, yeah. What are your thoughts about like the moon landing and like about a conspiracy of it?
Oh, the moon landing, okay. The original moon landing, well, I didn't even see it. I was a camp counselor that summer and putting little guys to bed. So I didn't take it very seriously at the time. I had no idea how much the human space program would affect science. I thought, well, this is just a stunt for the Cold War, which it largely was for Jack Kennedy. And now we see that human spaceflight program enabled the Hubble telescope to do its wonderful thing for all these 30-something years, and we needed it. So scientists' opinions about human spaceflight have changed over time because of that. So we're going to go back. This time we might learn a little more science from the moon, because we only landed a handful of places, and there's an awful lot of questions still open about this. What does the moon tell us about the history of the solar system? We still don't know how the moon was even formed. We think it was made by a collision of two planets. Okay, but tell me more.
Hello and thank you. Your idea about, or rather the concept of adaptive optics, your idea that we would point a satellite at a telescope, I wonder if you could elaborate on how that would better let us view stars.
I'm still having trouble hearing, I'm sorry. Could somebody repeat?
Yeah, of course. I was just hoping you could elaborate on the idea of pointing a satellite at a telescope for adaptive optics.
Okay, yeah. Right, so the tricky thing is getting the satellite into the right place, because it's flying around the Earth in an orbit, and you have to get it to be at the right place and the right time to shine down on the telescope when it's right in front of your target star. So that's the tricky, hard part. So it's rocketry, it's NASA science, it's NASA engineering to be able to do that. And actually, we do know how to do it, but we just have to buy the stuff and do it. So the same mathematics they use to send a probe to orbit around Pluto way out there, we just have it all written up into computer programs, and it runs, and it does it right now. But it's still kind of miraculous. Okay, more questions?
Thank you for your presentation. Over here. Hi. I also have a non-traditional question. I have a son who's a computer artist, and what he does is he's purchased pictures from Hubble, and he colorizes them and mirrors them. And when you look at it, untouched other than the colorizing and mirrorizing, it looks like people everywhere. There's faces. Have you seen that as well?
Oh my goodness, no, I haven't seen that picture. It sounds like lots of fun, and yeah, I'd like to see it.
I'll show you one at the reception.
Yeah, thank you.
Hi, yes. I'm a scientist also, and I am familiar with working on projects that might take, 1 year, 2 years, 3 years. You plan, you think. But I wonder if you could say a few words about what it's like to undertake a project that would take 25 or 30 years.
Yeah, sure. Well, among other things, it's kind of obvious it's a social thing. You're not all by yourself. You either can do it because of the support of the world, or you can't do it because you don't have enough support. But you see which direction to go, and you just start, and you work things as you go. That's how it feels. So there was never a dull moment. There was never a moment when we were waiting for somebody else to do something. It's just like work like crazy until we're there. And so it feels good because we're with a team. It's 20,000 people working together to do something together. So I never felt bored. I never felt tired. I just felt this is the coolest thing there is to work on. I'm going to work on it until it's done. So that's how it's been. So I love it. But maybe I should add that you can't do this unless you have the support network. If you're fighting to get your next dollar from writing a competing proposal, and you have to show that you've published something, you can't do this. So this is only possible because there's a system that enables it. If my thesis advisor had said, no, you can't escape until you get a next flight of your observatory, until it works right, I wouldn't be here.
Hi. I was wondering, what do you think are some ways that have been done or some ways that could make physics and astronomy more accessible to like children in schools or just like anybody, because it's like a very scary subject to people who are not in the scientific field?
Well, it's sort of rather broad question. My general thought about bringing children into science is encourage them to be curious. Don't tell them science is hard. Tell them science is fun. Turn over that rock and see the worms underneath and see, I shouldn't say this, see what they taste like. We should not tell them that. But to be curious. There's so much to be curious about. And if you tell them science is about this big fat book you're supposed to learn, they'll hate it. If you tell them these are the standards that you must meet, they'll hate it. Can you imagine teaching basketball by a book and you have to pass standards of learning for a basketball? We'd quit. We'd never do it. So science is something you do. That's how I look at it. It's not something you learn from a book unless you have to, like I did.
I have just a simple curiosity that why regular cameras cannot see and the James Webb can see. Is it just the filtration? What's the magic there in simplest terms, please? Thank you.
What is the magic of this? Yeah.
Or science.
Yeah, so, well, I think we have the opportunity to discover the secrets of the universe. And and I think the kids need to know that we don't know. That's what the cool thing is about science. We don't know. We're working on it. And you can read some of it in the book. You can see pictures in the magazines. You can read it on the internet. But our job is to do things that we don't know yet. So, I don't know. We've intimidated people by telling them that math is hard and science is hard. And it's a participation sport. It's not hard in itself. But we need to do it with each other, together. Then it's a sport. Okay. Okay, getting the microphone.
Thank you for the excellent talk. I'm curious, specifically with the James Webb Telescope, what is like your dream thing to discover or figure out?
Okay. The big surprises have been the galaxies grew faster than even we ever guessed. Okay, so we don't know why. we're still in process, but the spots are brighter, they're bluer, they're bigger than we thought they would be. So now we're trying to make sense out of little fuzzy dots with a spectrum, and it's a mystery right now. That's the biggest surprise so far. And maybe the biggest disappointment is we haven't found any little rocky planets with atmospheres. But, we can't argue with what nature does. We just have to find out what it is. But it would have been cool if there were little Earth-like planets out there, but not yet. Actually, that's one of the larger disappointments. We don't know any other solar systems like ours yet. We have 4 little rocky planets in the middle, then we have a gap, then we have 4 giant gaseous planets cold out there. None of the other systems look like that. So maybe, if that's an essential feature for having life, maybe life is uncommon, even if it always happens when it can. So there's a lot of questions still open.
How do you see things like AI and ChatGPT affecting your field in the future?
How do we see AI affecting the science?
AI specifically, like ChatGPT, things like that, affecting like your field?
Yeah, so people are learning how to use it for ordinary tools. How do I write a proposal? How do I write a paragraph? I tried, can you write a poem about quantum mechanics? It did. It was right enough. So you can play with it, but people tell me there's an awful lot of very simple, practical things it can help you with. We are getting a lot farther in artificial intelligence interpretation of pictures and models. We spend a fortune on calculating how the galaxies would grow. And now we find out the AI tools can cut the cost a lot. They can find patterns that we would not see. And then after you find a pattern, then you have to figure out what it means, but at least you found the pattern. So there's a lot of that going on already in astronomy, even before ChatGPT turned up. I think so far we do not have an artificial intelligence that has a genuine understanding of physical things. You can't say, creatures can walk. Even creatures with a brain that's the size of a pinhead can do things that the computers can't do yet. So that's because there's something different. And but I'm not saying it's not possible. I think it'll just take a little while. So maybe 5, 10, 20 years from now, we'll have something that actually seems to have meaning attached to all those funny words that it uses. And then we'll really see a tremendous change in everything that we do. Then we might be in trouble. I don't know. For decades, people have been arguing that there was a singularity coming, and other people telling us now that could never happen. Now something is happening. I guess you get to find out.
Unfortunately, we only have time for one more question.
Hi, thank you so much for coming. My question is, could you outline for those of us here who wouldn't understand this, many of us, maybe not my science colleagues, what the process was by which your failed graduate project became the basis for launching on, I can't imagine what kind of economic scale, a satellite that ultimately did prove what you needed it to. And that's going from graduate work to national budgetary issues.
Yeah, okay, it's an amazing story, actually. So ordinary graduate student project fails, we'll try it again. It works right the next time, by the way. The other graduate students and the professor made it work. So their budget's really small compared to the satellite budget. So, but how do great decisions in science projects get made? There are big committees that are established by big organizations like the National Academy of Sciences, and they write books about policy and what they think is the coolest thing to do next. And so There were committees that wrote, we should measure this cosmic background radiation better. They knew there was something in there to go for. And so the path was open when we sent in a proposal. There were already people who were primed to say, yeah, that's important. So even though we didn't know how to do it yet, they said, well, give them some money, let them start and see if they can. So it's a sort of step by step. You go from failed project to a proposal to give them some money to see if they can. Then if they get a little farther, then you give them some more money to see if they can do it better. And finally you get to, well, now we have a plan. We know how to draw this thing. We know we've done some tests. Now give them the rest of the money to finish the job. And so that's why it takes such a long time. From napkin sketch to launch, it was 15 years for that one. And we had to invent a few things along the way that we didn't have yet. So, but that's sort of the generic process. Start small, get bigger, hope to make progress, and you could die at any moment if you can't actually carry out your promise. So a lot of projects do die. You just don't hear about them. The professors weep, but
Okay, before we conclude tonight's event, I just want to remind you all that there will be refreshments in the lobby. And with that, please join me in saying a huge thank you to Dr. Mather.